Alright. Hope that worked. I guess we're about to find out. Excellent connection. Alright. It's an excellent connection, chat. We're fine. It's all good, chat. Chat, my 0 viewers. Let me put my phone. Yeah. It's 7:35 in the morning. That is irrelevant to everything else. I don't know why I mentioned it. But it is 7:35 in the morning. It's still 7:35 in the morning. It's still 7:35 in the morning. It's still 7:35 in the morning. Why can't I click it? Is there a gyating issue right now? What the gyat is happening? I can't click it. Oh my god, no. I clicked the chat. It's all fine. We're fine. Calm down. It's all gonna be okay. Let's go to battery. Battery. Low percentage mode. I'm gonna go back to YouTube. Alright, chat. So let me explain what's happening here, chat. My chatty chat. I did not lie. I did not stutter. You heard me correctly and rightly as well. I'm going to be trying over the course of the next few streams to make a functioning computer in Roblox. So, I mean, honestly, this is probably the craziest thing I've ever tried to do. I will be limited in a lot, and I'm gonna go in here to show you the rules. I haven't fully made them. I might make some up as we go along. But a lot of this this stuff is really strange. So rule number 1, basic. Right, I'll just use text. Basic things only in terms of the coding. Basic coding only. What does this mean? This means no like really strange or complex stuff. Basically, you know, if you're doing anything too fancy, don't. And all references need to use an internal system. What is it? Like an internal hierarchy. I spelled that right. So what that means is every object in the script needs, if it's referencing to something such as a wire, it needs to use its own internal hierarchy. Code cannot be shared without communication between we're typing between simulated integrated circuits. What does this mean? If you're using the CPU, you're coding in the CPU core 1, you cannot get information from the BIOS without a physical serial communication, meaning that you need to establish communication with the BIOS chip, and you need to use whatever custom transfer protocol we're going to create to talk between the CPU and the BIOS, right? No, you can't. What this means is the CPU needs to ask things, and well, it depends on your transfer protocol, and I'm going to be making my own custom one for the sake of this video. And I think today we're mainly just going to be setting up all of the circuits, all of their actual components, like visually on the without any coding. We're going to be labeling them and organizing them to make some things easier. But for the most part, they won't be relevant, and it's mainly for organizational purposes for when we started coding the main module, the parent module. Parent module. What does this mean? Parent module. Only code item accessible by all code structures. All scripts can access this. Why? Or sorry, only code item where relevant. event. I can spell, guys. All right. Relevant items are available by all scripts. What does this mean? If, for example, I wanted to create an arithmetic operation in 1 plus 1, which will, because this is something that needs to be calculated, I will be coding my own logic gate system to handle calculations like this and converting it into binary for an output. So this is going to be very down to the bare bones, basic coding things only. However, if I create a function do 1 plus 1, and I have all that stuff, I've already made that, right? I've already made that. I don't need to make it again for every single script or every single relevant script that uses that. So what does that mean? If relevant to script can be shared and added to parent module. So the parent module is only for organization. I'm only going to be using that to organize things. But the parent module will be useful. If I already code something, I don't want to code it again, all right? If I've already coded all of the code for one core, I don't want to code all of it again, and I probably won't because of how I'm going to be coding that in the first place. If I want to do 1 plus 1, I must, once again, like, if I want to do 1 plus 1, I need to do the 1 plus 1 function, or do whatever function, and that function will be going through, it's going to be complicated, basically, because if I want to calculate 1 plus 1 for, let's say I'm doing a calculatory operation, and I get the do 1 plus 1, or I just have another script that wants to call it. 1 plus 1 is a CPU operation. This means it'll be in the CPU whatever, right? CPU functions parent script. However, this stuff, although we can use this parent module, which will have a bunch of like mini modules, one of them being the CPU functions module, maybe. To send this, you need to send this in serial. You need to convert the result, or not convert the result. You need to ask it. You need to send it a serial message. It needs to be, when I say serial, I mean you need to convert whatever you want to send it into you need to establish a custom communication with the, for example, the CPU. If you wanted to tell the GPU to render a 256 by 256 image, you would have to establish communication. And for the GPU, another high importance components in the quote-unquote, simulated computer, I will be using a custom communication protocol with more available lanes. The communication protocol I'm thinking of for a lot of the things is just going to be a one byte or 1 byte 8-bit per clock tick. Basically, it's going to be 8 what are they called? 8 the things, 8 pins, quote unquote pins. Once again, this is all simulated. There's going to be 8 pins, and each of these are going to send either an on or an off signal. Once again, this is just the planning stage. This is going to take a very long time to get this computer down, and there's no way I'm finishing the next 4 or 5 streams. So each of those pins, we send a signal on, 1 or 0, on or off, power or no power, and we do at each tick. There's not going to be interference or anything. Like I said, this is very rudimentary, very simple. Let's see, what else we got here? For the GPU, I'm planning in other high importance components like the audio chip and the monitor. That's right. The end of this, I want to get audio output. I want to get display output via the GPU. So for those high bandwidth situations, I will be using a different communication protocol. Once again, I don't know what I'm going to do. We'll cross that bridge when we get to it. But sorry, if you were expecting coding in today's stream, you've been mistaken. Today we're just building out the blueprint and getting the actual visual representations ready and organizing the hierarchy of some things. So next stream we will hopefully hopefully again the actual coding part. But let's see, what should we start with here? Sorry, God, I told you all the rules, but I didn't even tell you what we're doing. Let me tell you the actual highly confidential plan here that I have for the CPU. Or I say CPU, but this is the entire computer. But the CPU is the by far the biggest part that we're working on here. It's by far the most important part. So we have this, wow, high quality drawing here. This, all right, we have, and these two, right, they're connected, believe it or not. We're gonna have this, right? I know you're thinking, wow, this all looks so cool. You're so cool. And, all right, I promise these lines are important. Okay. Yeah. All right, we're gonna have you here. And this is all completely custom-ish. Maybe there's some stuff. You know, great minds think alike. And you will be sending these. And these are simulated actual communication lines, data transfer lines. Once again, this is on the planning phase. And this is where the, assuming here, this is going to be our input. Now, I'm not sure how many lanes are going to be here, but it's probably going to be a lot of data coming in through here. So I'll make it big like this. I'm not sure. I'm thinking of having you know, a massive 8 what's it, bits, whatever. Who cares? 8 bits a second are going to come through here. So that it's going to be an 8-bit processor ish. So 8 bits per second I think is going to be what this data lane is going to handle, which is going to be the input lane for the CPU. This is where commands are going to come from. So commands are going to come, this is, I'll call this the, what's the fancy name we're going to give this? We need an acronym, chat. Does anybody have an, oh, there's 2 people watching, nobody has an acronym. You know, I hate all of you. Unsubscribe right now. I think the other person actually just beat me. Okay, let's call this the, watch this, guys. Oh my god, that scared me. Okay. Processor input mass data line. Here we go, chat. Here we go. Now this is high quality. PIMDL. Oh my god. This is, wow. I mean, have you seen anything more impressive in your life? The PIMDL, chat. So the processor input mass data line. This thing is going to send in the commands, right? The commands, the instructions even. This is basically going to send in everything. Everything, all inputs to the computer are going to go through here. And now all inputs to the computer are going to be custom microcode. It's going to be coded in a custom microcode, custom microcode language, converted to binary. So all the inputs in here great handwriting here. So all the inputs to the processor are going to be in a custom microcode language converted to binary. What that's going to look like, I don't know, but I have a few ideas. So it's going to go through here. We're going to have all the zeros and ones coming from this processor mass data line. All the information from the processor mass data line is going to go directly up to here. This is the CPU part of the CPU. I call it the command core. There's 3 cores, and I consider this one a core. I cannot write for some reason. Command core. You may be saying, wow, this sounds like a core from Portal 2. And that's because it is, actually. Anyway, what this does is it does the handlement and division of labor throughout the entire system. So the communication protocol, and this is how it works, right? There's going to be, and this one is going to be a, let's just say a two packet data line, right? We can send 2 data transfers at a time through here. So this is 2 bytes. 2 bytes. And what we do is that this is nothing special. This is just communication to here. And what this is the core management core info. Sorry. Core info controller. Core info microcontroller. What this little thingamabob is going to do is it's going to give info to the command core and other stuff, which we'll figure out eventually, to help the division of labor. The data is not going to be sent through here for semi-obvious reasons. It's just a lot of data, and it will be more efficient for the command core to send the data directly to the core. But it is very important that this thing is right. So what we're going to do is send a command over. The first thing that the command core says to the core info microcontroller is, hey, is there an available core? Or, well, mainly, what they should do is establish communication. Say, hey, are you busy? No. Actually, no. We want to keep it as little words as possible. So we can give 2 bytes of data. So what we can do is a quick call to, let's say, we get info from the input, right? Let's say it wants to do an arithmetic operation. One of the inputs that we get, and there is cores, but each packet that is given from the inputs is handled manually, right? So let's say we get something and we get a command, right? Dot, we get this dot, right? Now, we don't know what to do with this, right? But actually, we do. As soon as we get the dot, we look at it, and immediately, we need to keep this, right? So what we do is the command core sends this to the core info microcontroller. So the core info microcontroller takes this, and it has the dot. Then it's going to be dot, which is the data, right? This is the data part of the message, and C. Now C is an abbreviation for cache. So we're going to send .c over here. And what the core info microcontroller here is going to look, and this is 2 bytes, so we're able to send both of these. It's going to look at the C, and it's not even going to care what the first thing is, right? It doesn't care about what the first, it's dot in this case, but it doesn't care. Dot is a prefix, by the way. The command core can handle this after it's in cache, because it needs to remember the information, right? You forget when you're programming that whenever you get this information, it needs to be stored. All variables that we define need to be physically stored somewhere with enough available space to store the information in the variable. So that's very important that we keep track of that, and all variables are going to have a tally of how much data is actually contained inside of them. And if we store, let's say we have a 256 byte cache, and we store 257 bytes, what's going to happen is that I believe in this case it would still be referred to as a stack overflow, and the entire system would shut down. The entire thing would stop. So, and that's not going to be any core. That's just going to be the game kicking you out and saying there was a stack overflow in the cache, because I just want to make things easier on myself. There's no reason to do a bunch of fancy animations or break everything in a way that doesn't make sense. So that will actually, I don't know if we should do that because it might be better. Well, we'll have a visual representation. We'll see what happens. So this right here is the cache. The cache is like, if you know what DRAM is, it's a temporary memory for the CPU to access stuff instantaneously. This is stuff it needs right now, and it's going to be using right now. So whenever it says .c, it doesn't care because we need to speed up this very process as fast as possible. It just sends that data straight to the cache. Or sorry, I'm lying. I tell a lie. First, what it does is it needs to make sure that the cache has room for it. And the way it does that is instead of, and what I was thinking of is asking the cache, but actually, it stores. Oh my god, no, it cannot store anything. I keep forgetting. I was gonna say it stores an internal memory of everything that was put into it, but that would need a cache in itself, a cache capable of memorizing that. So we could have a cache. Okay, no, so the first thing we do is we ask it, we send out a request to the cache for available space, right? We say, hey, do you have any available space for us? We're sending a message to the cache. Is there somewhere I can put this? I need to put it now. Do you have somewhere I can put it? If the answer is no, right, it does not have an available place to put it, then it will return saying, no, I don't. If it says, no, I don't have an area to put this cache, the core info microcontroller will send a code back through the command core saying, hey, N. This means no. The cache refused to store it, and if applicable, we may have a debug code. The debug code will be temporary as it takes up bandwidth. So if it says yes, though, which is going to be the majority of the time, considering we do what we're doing properly, if it says yes, then what we're going to do is, and it's not going to just respond with yes, it's going to respond with yes and a table of a table of all available spots the core has, or yeah, all available spots on the cache. And now for sake of sanity, we're going to be assuming each chip is a small cache capable of storing data like a table that it's only going to be using for like 3 seconds. Very like, and I don't want to do that. The issue is with storing and managing data to the cache, you need data to store the cache in. So what we're going to do is, let's try this again. We're just going to send the data to the cache, and the cache is going to have an internal reservoir. This is going to be like a cache, right? The cache is going to be managing the cache, and it's going to have a little cache managing microcontroller and a little bit of it reserved to the cache. So in the cache, we reserve a table. We have a table of every position available and non-available in the cache, as well as their orientation and data received. So basically, what order was it received in, right? And yeah. So what we're going to do is we're going to send a message to the cache microcontroller. The cache microcontroller, hey, I have this data, C, or in this case, dot, and it's going to be S. S is going to stand for store. So the cache microcontroller sees this, and what it's going to do is, now that it has a memory, a small memory of the cache, what it's going to do is it's going to say, hey, cache, does the cache over here have space? And if the cache says, because it has a table of everything going on inside the cache, no, it doesn't, then the cache is going to tell the cache microcontroller, which is also the cache microcontroller, no. And it's going to once again send that end signal, which is going to go up to the command core, and it's going to I actually don't know what it's going to do if it fails, but probably just stop working for now. If it does have a space available, though, it'll store it. The cache microcontroller will the cache microcontroller will tell the cache, right? Okay. If it's yes, do you have space available? Yes, there is space available. And it's more of the microcontroller asking itself, because these are all one unit. Do I have space available? If it does, it'll store it, and it will respond to the command core with two very important things. Dot, in this case dot, and then a number. This number is going to be the index in the table. This is going to tell the command core, okay, that looks really weird. This is going to tell the command core, hey, this is where the data is this is the index of the data. This is its ID. This second number, 1 byte, is going to be the ID. And you can tell this is a very small cache. It might be necessary in the future if we're planning on expanding the CPU beyond having a 10 byte cache or 10-bit cache to increase the data lanes on this thing right here. And right now, quickly, this is assuming that we're saving one piece of data at a time. This 2-bit lane requires. If we had a 4-bit lane, we could save 4 bits of data at a time, which means right now we have plenty of input power, but not enough power to save information in the cache. meaning that we do have a bottleneck right now when it comes to this 2 bytes per 2 bytes. Ideally, this would be 16 bytes, which it might be in the future, but for simplicity's sake, I'm going to be keeping this at 2 bytes, and I'm probably also going to be keeping this temporarily at 2 bytes, just to make things easier when it comes to the programming. This will be restricted to 2 bytes for now. So we're going to send a dot, which is the object sent to us, and a 1. Now the reason we're sending this is we're sending two pieces of information. The dot to confirm to the controller that this is what, this is what was stored, right? This is what you wanted me to store, right? And I'm starting to think we should get rid of the cache microcontroller design and give each core individually its own cache and then a collective cache for the cache of the caches. I think that might be a good idea. But I feel like the cache with the cache and the cache microcontroller is fundamentally how all the caches are going to work. This is an outline for how all the caches are going to work, so this is a really complicated design, really. No, not you. What did I delete? 2 bytes. All right. So, yeah, what we're gonna have here is a cache for the the controller. This is going to be a small one, 10 bytes, and we're gonna have a really small. This one will be 2 bits, equivalent to this. So, if this is X transfer, this is also XT, meaning that these will have the same transfer rate, making everything really easy and reducing bottlenecks. I'll put this little symbol here to signify that these are the same, or that they're variables. For now, the X transfer rate is going to be 2. Meaning right now this computer is operating off of, this will currently be a 2-bit computer. All data transport like this will be done by the same metric. So this is a version of the cache system specific and all the this controller, I think this will be more focused on core info, and I feel like I will be repurposing this one, the a cache microcontroller, to also be a cache microcontroller and the cache management microcontroller. So the command core, instead of interfacing with another core in between and then to that, we'll be referencing this microcontroller, and I'll have that signified by a line here. It'll be referencing this microcontroller specifically, and this microcontroller will handle everything. So this was the microcontroller. I reference this by sort of this symbol, I reference the mini microcontrollers by this symbol. Then the cache will be marked by an X here. So this is all a cache. And like I said, cache in this context is super fast memory that's being stored very temporarily. And by the way, when I say like your number in line and confirming, it's going to send like a dot and it's going to send the number. This is just for you to see. The real computer will be seeing this in binary. Of course, it'll be seeing it in it will be 16 characters. It'll be 16 bytes, but 2 bits. And as we increase the bandwidth of the computer, this will also increase. Okay. So, what's going to happen is, let's say the computer, in its current 2 bytes, gets an input, right? Dot. And it's just going to get a dot, and when we get one of these, we are going to keep the next line blank. Right, so this next line will be blank for now. Yeah, because this is 2 bytes. So the first one will just be a dot. Because the command processor is going to look at this, and it's going to do one thing, right? It's going to look at a predefined list of stored commands. This predefined list of stored commands is going to be stored And because this is static and non-changing, this will be stored inside of a chip. I was gonna say SSD there, or the disk space. It would, I guess it would be an SSD because, well, I wonder. The Roblox servers probably use SSDs, but who cares, right? But it will be stored on a virtual chip. This chip will be the microcode chip, This will be predefined. This is just like a storage drive, right? This is storage. I'll make storage by this symbol, which will kind of be looking like this. This is a storage device. It's going to be basically saying, and this is the microcode in microcode controller. Actually, no, we're not going to be using a microcode controller. Actually, we'll think about it, right? So we have microcode here, microcode. This is basically going to tell us if we don't know what to do with it. So, it's basically going to be looking through here and telling us what it means. So we are going to have a little microcode controller here. That's what our controllers looks like. So what we're going to do is with this XT transfer port, this XT transfer port is going to be connected to the command core. A lot of stuff connected to the command core. It's going to have a lot of outputs. And basically, when the command core gets a command, it's going to be sending a message to the microcontroller storage device. Well, actually, it shouldn't have to. It should be able to process it itself because it's in direct communication with it. All right, I'm sorry. Yeah, we can get rid of the processor aspect of this. We're actually probably going to move it because more realistically, the microcode controller is probably going to be within the command core itself. So what it's going to do is the command core is going to get this message from here. It's going to go here and ask, hey, is this, what do I do with this, right? Or no, it's going to loop through each instance of the microcontroller, and this will be, even though it's inside the chip, it still needs to talk to it. So this will be at 2 bytes per minute, meaning it will be able to look through stuff with 2 bits of data per minute, meaning probably just what it is and what to do. So, and yeah. So it's for now, we're going to go loop through it. This is going to be in binary, obviously, and it's going to be returning either an S or an E. So S means store, and E, and by the way, these are going to be not S and E, these are obviously going to be different identifiers, probably just complete zeros or complete ones, or just a 1 and a 0, which might actually be what I'm going to do. I can't believe I didn't think of that. These are just simple signifiers. They don't need an entire bit to represent them. So it's going to be a 1 or a 0, or combination, or like a 1100 or 1010, which could mean different things, but right now the current instructions are going to be 1 and 0. 1, if 1, then we're storing you into the cache, right? And yeah, we're storing you in the cache. If you say the cache microcontroller is going to be like, okay, I want to save you in slot 1, right? And then the next step is going to be what the next input is, right? So let's say the next input is .e, right? This is an E. I can't erase it. We get an E. E doesn't have anything specific to it. It's just a letter. So when you go through here, by default, when the microcontroller doesn't know what to do with it, or the microcode controller doesn't know what to do with it, it's going to by default be giving out a 1, meaning store it. And so it's going to, we have dot already saved. Now we have e saved. And now that we have dot and e saved, we're going to be getting the all important, most important identifier at the end here. So dot e, I'm not sure if it's a real command yet. Once again, this is all just a thought. Dot e, or sorry, semicolon. So if we get a semicolon, the controller recognizes this and it actually is going to output a 0. So we're going to get a 0 now. So what does this mean if we get a 0? Well, it's actually, we're going to be removing this arrow, and, well, actually, we're not going to be removing this arrow. We're going to be sending a different signal. And these 2 bytes we would usually send is the info we want to send in a 1, as in save it. But instead, we're going to be sending an entire signal of all zeros. We're going to be sending, or not all zeros, I'm sorry. We're going to be sending a signal of all ones. All ones basically means, hey, we want to pull from the existing data, and you can go ahead and delete that data too. An alternating 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1 would mean, hey, we want to pull from that data, but don't delete it. And 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, which is the inverse of that, would be delete everything, we don't want the data. So that's the communication scheme for the cache. That's how the cache and the command core are going to communicate. But we're going to be doing all ones, which means we want the data, but you can delete it. So what we're going to do with the data is we're going to be, now that we have this data, which is going to be dot e, by the way, so this actually needs to be more than the input rate. No, it doesn't. No, yes, it does. Because if it's not, then we're going to need a cache. And if we are using a cache, then this isn't going to work. You need a cache in the controller. So let's do x times how many, there's going to be 10 parts of this. So x times 10 here. We want to do 10 times the transfer rate. So we can transfer everything all at once to the microcontroller. So everything all at once gets sent to the command core in order, of course, that it was in the order that it was saved. It will always be in the order that it was saved. Usually we'll delete the data after we're done using it, as to not to clutter the cache and get confused with the information we have. Also, if we try to store too much data, which hopefully should never happen, the cache, I'm not sure, the cache will not have anywhere to put it, so it'll send back a signal of, I'm not sure what it will send yet, but it'll send back a signal basically telling the command core, you know, it's not going to know what to do with it, so the processor is going to be like, you know, in the microcode controller, it's going to have this data saved in there also. It's going to have a lot saved in here. We can just only reference so much at a time. So this will be an interrupt, meaning that this takes priority over current functionality, and we can go ahead and pause this, and we can take priority and ask the microcode storage controller, what does this mean? And it'll recognize, oh, that's the command. You know, we'll do the same thing just with the commands. That's the command that means you're screwed. That's the command that means, you know, the cache is, you're trying to overflow the cache with information it doesn't already have, meaning that the command is corrupted, the microcode has failed, and now the command core is now unstable. So what it'll do is it'll send back a code to the command core. It'll send back a central importance code, which will be identified with some of the last bit at the end. Will define whether or not it's one of those codes, and the command core will then shut down. I don't know how that's gonna look. It'll just stop working because the computer, the CPU is now unstable, and it'll probably just stop the entire simulation and throw an error to the console saying command core cache overloaded or whatever, or microcontroller storage reports cache overloaded, or microcontroller storage gave back shutdown command because cache reported overloaded, which microcontroller confirmed. Whatever, we'll get there. We'll cross it when we get to it, right? So yeah, we save everything in cache. Once we get the semicolon, we know, hey, we need to take this command and process it. We take it out, and we need actually more lanes on here, or else we need to put a cache in the microcontroller. So once we have all that, we'll have a, what is it? Yeah, also a times 10-bit lane, times 10-bit lane to the information that comes out of here. Basically, we'll send it straight to the microcode controller, and then it'll tell us through a series of binary what we need to do. A lot of the times it will, and basically, right, we need to store this. The microcontroller will give a command that will tell us to store information in the cache, and the information in the cache will be like an alternating series of numbers, which fed to the microcontroller cache again, followed, we feed to that again, which we can just ask it. Really, the microcontroller isn't doing much here. We're just pretty much asking it stuff, and it's telling us. If it's this code, then we know we need to do, let's just say, arithmetic. So we figured out through this painstaking process of going through the cache that we want to execute 1 plus 1, right? We figured out we want to do this command. This complex series has led us to believe we want to do 1 plus 1. All right. So what do we do? Now that we have a full stop and we know that this is the next command, this will be identified by the processor input mask data line giving us all ones, meaning that we are done with that command. Let's move on to the next one. And what this will do is it will send the data through to here down to the core management controller with the information. So it'll be like some certain binary code for addition, and then it will be the actual numbers that want to be added together. The core management thingamabob will then send a busy signal to each of the cores. Basically what this means, it'll ask the first core, are you busy? If it responds, then it's obviously not busy. So then it'll send the addition to the core. If it asks the core, are you busy, and it doesn't respond, well, it can't respond. Do you know why? It's busy. So it will ask the other core. If both cores are busy, and I'm sorry, this data will then go over here, be stored in the cache, right? Keep forgetting about this thing. We need to store it in the cache. So 1 plus 1, well, 1, 1, and like some other stuff that signifies, oh, we want to add, basically, right? 1, 1 in addition. So we know we want to add. So what we'll do is, and I'm sorry, we need to save this in the first number. First thing should be add in the two numbers that want to be added together, right? So what we'll do is we'll ask the controller, we know we're busy because we know we want to do something because the CPU transmitted a signal on one of these data lines that says, so we actually want to be, this one wants to be x plus 1, x times 10 plus 1, an extra data line, which is going to signify you're doing something. Oh no, I'm sorry. After each data transfer, and it needs to know this, so all this microcode will be stored over here. This will be the microcode, and it will be connected to everything that needs to use it via, these big, large data transmission lines. And basically, it'll get transferred, everything will get transmitted to it, and it'll know because every time data transmission comes, it will check, if this, then, we check here, then we go ahead and we get this, we feed it all the way to the microcontroller over here, and it will output, hey, we need addition, you're expecting three numbers or three total items stored inside this cache, and you're expecting the last two to be numbers. So this will go back to the controller, or it will go back over here to here, and it will loop through all of these, still looking at them, and it'll see, yes, we have plus, we have one, we have plus one and one, which will each time a data changes happens, actually, it will go ahead and send this over to here, and it'll say, hey, I don't know what these last two digits mean. I don't know how to do this operation, but I know the first item in this bit chain means do addition, and I know you have two other objects identifying as numbers. So you want to send this to one of the cores, and it will respond with a number, which means like 1010 or something, which basically means send data to core, right? And if responds to that, it'll send a busy signal to one of the cores. Like I say, we'll do the same process, check if it's busy. If it's not busy, then we'll check the other one. If it is busy, if both are busy, then, and we'll again have to store that this is busy in cache. So if busy, then over here, we'll add in a separate reserved part of the cache for system operations. We'll add this, and once again, we'll be referring to the microcode to figure out how to do that. We'll be sending in here T, or in like T, and we'll check here if there's two data entries in here, and we basically send these bytes to here, and the microcontroller says, yep, they're both busy. Then what we're going to do is we're going to wait a clock cycle. We're going to repeat the process, and we're going to wait a clock cycle. The microcontroller is going to tell it to delete these two and to check it. So it's going to be like 1010101, and this means delete system cache, check both of these. It's going to repeat this process until the cores aren't busy. If it receives data from the command core during this process, then it can't execute it. So the data, it will basically, each time the command core receives something, it'll send a response signal saying, I got it, right? If it does not send this, it means it is busy, likely trying to wait for a core to be available to do this processing. And what that means is it goes back in here, the command core recognizes this signal via the microcode controller, and the microcode controller tells the command core to stop what it's doing, right, and send this information all to the cache, right? Send this information to the cache and stop what you're doing. So it's going to be like 10101, and just store it to the cache, right? So it's going to store it to the cache, and it's going to figure out how to do that by asking the microcode controller what all the data it just got means. It's going to store all this to the cache, right? And after it stores all that to the cache, it's going to once again go back here. It's going to do the process again each clock tick, and if it receives the same thing, it's going to keep going in between cache, until eventually this thing frees up. And once it does free up, this will be able to go through. It'll be able to allocate it to a core, and it will be able to wait. Now, the cores should be very quick. There's no reason it should be stuck in a process for more than like any amount of time. This is really quick. It's not going to be getting complex problems here. It's going to be getting 1 plus 1. Now, it is time to delve into the logic circuits, because to calculate 1 plus 1, we need to do logic stuff. So each core is going to have a section called the APU. This is the arithmetic processing unit. I'm not exactly sure how we're going to get this to work. It's also going to have a microcode connection, meaning it's going to be connected to the microcode controller here, which is going to, and this is a large storage device, the microcode controller, which is going to give data, and it's also going to have a mini controller inside of it to handle indexing of itself, right? So we're going to do that. It's going to go in here. It's going to basically say, what do I do, right? We're gonna have the APU, the arithmetic processing unit. It's going to get its instructions from like the machine code. The microcode here is it's basically going to tell it what to do. So it's going to get an input. No, I'm sorry. Yeah, okay. So for the sake of easiness, I'm going to be assuming each processor cannot store memory on its own. The only memory it can store on its own is its own program. Its program, unless dynamically changed, can be stored on the own processor without a cache, which is something these MCs were for. But that's overcomplicating things, and it would cause an infinite loop of needing one. So I'm just going to say each one of these chips has a built-in MC and built-in processor. It's assumed it knows already what its code is unless it dynamically changes. For instances revolving around storage and grabbing things, the MCs or like solid storage devices will store the code, right? It'll store like what it'll store how do I describe this? It'll store not the code, I'm sorry. It'll store the data it needs, right? This will tell it like like assuming the processor gets like 0001 1100 1100, the APU will ask the processor what's in its registry for 0110. It will return addition, right? And or actually, yeah, it'll return addition. So, but it can't check that, so I don't know how we're gonna do that because you need to ask Matt to do that. Whatever. I guess it'll just return a series of logic gate operations that it needs to perform. The APU will perform the operations, and the output of it will go to the data output lane. And the data output lane, where's the data output lane, chat? The data output lane will somehow connect to the core management controller. Now, after it's done, it'll go to the CPU, the core unit, which will then be sent to the core processing unit. This is what handles the cores. It'll have the data tagged as an output, and it'll send. I guess what it will do is send the data back to the command core as an output. So the data will go up here. It'll go back through here, and the information will be marked as an output. This is going to have some more lanes, and the output data will it'll check what to do depending on what the operation performed to it was. So it'll in the serial input over here will tell the command core what to do after via like 0110 1110, what to do with the data after it gets it. And there's a lot of possible scenarios here. One of them is outputting it, right? Just straight up outputting it out of the data line. So it'll send the information back through probably a processor output mass data line, another data line, which will do something, I guess. I don't know what the output data line, it's going to do something. Assuming it needs to save the data, it'll save it in random access memory, the DRAM, the dedicated random or the dynamic random access memory, where it'll then be mentioned later on. I have a controller chip saying, hey, this is it. I'm here. Hi. It'll save the location of it in in a mini chip. We'll figure it out. We'll figure it out. We need to save the RAM in there. We'll figure it out. We'll figure out how we're going to save the RAM in there. But basically, we'll save it for later in RAM quickly. And then once we need it, yeah, that might work. But yeah, once we need it, we'll save it. We'll come back to it and do whatever we need to do to it. Either everything's going to go out that output line, everything's eventually going to have to get out. Things are going to be sent to the GPU and sent to the GPU there. I don't care about them anymore. The GPU will handle it. There's not going to be any GPU CPU intercommunication for the simple fact that it's too difficult. Maybe in a future version of this project we'll feature GPU CPU intercommunication, but for now it's just going to be CPU to GPU communication, and the GPU will directly output via the display line, which connects to the monitor. That's going to be pretty easy, the GPU, in my opinion. We're going to get it's going to be a massive data line from the CPU to the GPU, kind of like a PCIe slot. You know, see those are really, really big. They have a lot of connectors and stuff. And it's going to basically go through pixel by pixel, assigning each pixel to a core. And then each core is going to do the calculation for the pixel, given the data provided. There could be a lot of outcomes here. Like, yeah, we'll see. Basically, there's a few things. The command core should just do like an as told mode, meaning I just got this data, do it as told. Meaning just put the pixels in an array like is being told here, meaning that there is no real computation occurring. Not really, at least. The data is just being transferred. And the GPU is with the data, it's turning the binary into color data. So I guess there would be some computation involved using the binary decoder. It's then outputted to the display, where the display will display it. And I mean, sure, we'll have an FPS value on the display. That won't be part of the system. Just a fun thing as well. Thinking of other things. This is a complex thing I'm doing. That's all I got right now. My God. Well, that was my. Don't worry about the Gacha Life screenshots. That was for something else I was doing with my friends. Believe it or not, I don't do Gacha Life. And that's it. Well, if you somehow enjoyed that, right? I'm sorry. I'm sorry that you felt enjoyment out of that. In the next video, we're going to be building it. I said we're going to do it in this video, but honestly, I feel like we did so much in this video just kind of pseudo planning out what we're going to do. In the next video, we'll actually start working on it.